Welcome to my presentation. In this presentation, let us try to see how we can solve system of linear equations using inverse of a matrix. Okay, so the concept here is as follows. If we have A as a matrix, and if we were to multiply that by a matrix X, we're going to get a constant matrix B. So A times X is equal to B. That is the way we can represent a matrix equation. And then if this is the case, we want to find the value of X, and the way to get that is by writing it out as follows. X is going to be equal to inverse of matrix A times the values what we have for matrix B. So let us see if we can achieve this by solving this example problem. Let's say we have an example of this type. We have a system of linear equations here. The linear equations are given to us as follows. 2x plus 3y plus z is equal to 1 is equal to -1, let's say -1, and then 3x plus 3y plus z is equal to 1, positive 1, and then 2x plus 4y plus z is equal to -2. Let's say this is equation number 1, this is equation 2, and this is equation number 3. We want to find the values of x, y, and z, and this time we are going to use the inverse of a matrix to be able to achieve that. Okay, so let's get started. In this example, we're going to use the Gauss-Jordan method to find the inverse of a matrix, and then we'll use this matrix equation to be able to solve that problem. So the way we can write this coefficient matrix from this system of linear equations is as follows. We can write this as 2, 3, 1, 3, 3, 1, 2, 4, 1. These are the coefficients of x, y, and z in equations 1, 2, and 3. And then times the x matrix here is x, y, and z, and the constant matrix are the numbers on the right hand side of the equal to sign, which is -1, 1, and 2. Okay, so this is the A matrix, this is the X matrix, and this is the constant matrix B. So let's start to apply the Gauss-Jordan elimination method. And in this method, if we have a matrix A and we're going to partition it with the identity matrix, and the way to write that is as follows: 2, 3, 1, 3, 3, 1, 2, 4, 1, and then we partition that with an identity matrix which will be a 3 by 3 matrix now, which will be 1, 0, 0, 0, 1, 0, and then 0, 0, 1, like that. This is our A matrix right now, and then this is our identity matrix. When we transform this, when we use Gauss-Jordan method and use the row operations to achieve that, it will so happen that the identity matrix will be on the left hand side of the partition like this: 1, 0, 0, 0, 1, 0, 0, 0, 1, and then on the right hand side we will have numbers or elements A, B, C, D, E, F, G, H, I. Those could be numbers, and therefore this will be our identity matrix on the left hand side, and this will be our inverse matrix, and that is what we are looking for. We will achieve that by using this Gauss-Jordan method. Okay, so let's get started. In here we want to make this location equal to 1. To achieve that, we're going to perform the row operation, And then the way to do the row operation is as follows. The new R1 is going to be, let me write this like this, the new R1 is going to be equal to minus R1 plus R2. So we're going to subtract row 1 from row 2, every one of the elements. When we do that, we get 1, 0, 0, and then we'll partition this. Then we have negative 1, 1, 0, and then in the second row we did not change anything, so therefore we have 3, 3, 1, 0, 1, 0, and then 2, 4, 1, and then 0, 0, 1. Okay. Then next step, we want to, let's draw this line along the major diagonal, and then next we want to make sure that we get a 0 in that location, and to achieve that we're going to perform the row operation, and the row operation we want to do is as follows. The new R2 is going to be equal to 3 times row R1 plus R2. First we'll write this row and then we'll come back and then fill up the rest of the rows. So we have here 0, 3, when we perform this 3 times row 1 plus row 2, and when we perform when we apply to every one of those elements, we get 0, 3, 1, and then we'll put the partition there, and then we have 3, negative 2, 0 on the right hand side of the partition, and then this is a 0, not an 8. Let me clean that up. And then in the first row we have elements 1, 0, 0, and then we have negative 1, 1, 0, and then we, in the third row we have 2, 4, 1, and then we have 0, 0, 1. So we successfully completed the row operation here. So let's draw this finish line along the major diagonal, and this time we want to make this location as equal to 0, and to achieve that we're going to perform the row operation, and when we do that, this is how it is going to look like. So the new, let me write that row and then we'll come back and then fill up the rest of the rows in there. The new R3 can be achieved by taking 2 times row 1 and then adding it to row 2. So when we do that, we're going to get 0, 4, 1, we'll partition that, and then the right side of the partition we will have 2, negative 2, 1, and then the first and second rows will be the same. So let me write that. The second row will be 0, 3, 1, and then 3, negative 2, 0, and the first row will be 1, 0, 0, and then negative 1, 1, 0, like that. So now let's draw the line along the major diagonal, and this time we want to make this 3 equal to 1, and to achieve that we're going to perform the row operation on the second row, and when we do that, this is what we're going to come up with. The new R2 is going to be equal to the new R2 is going to be equal to R2 plus R3. If we do that, we should be able to achieve that and make that location equal to 1. So when we do that, we get a 0 there, a 1 in that location, and a 0 there. We'll partition this, and then on the right hand side of the partition we will have negative 1, 0, 1, and in the first row we have 1, 0, 0. We didn't change anything there. Then we have negative 1, 1, 0 there, and in the third row we have 0, 4, 1, and then we have 2, negative 2, and 1. So that is how it transforms to when we do the row operation. Let's draw this line along the major diagonal. We have 1s along the major diagonal, we have zeros in these locations, and the only place we want to change it is this 4. We want to change that location to 0, and the way to do that is as follows. So we're going to do a row operation on the third row, and the way to do that is as follows. The new R3 is going to be equal to 4 times R2 plus R3. That will do that. That will make that equal to 0. So this will be 0, 0, 1. We'll partition the line by drawing a line there, and on the right hand side of the partition we will have 6, -2, and -3. I'm achieving these numbers by simple addition subtraction basically. And then the second row we have nothing has changed, so therefore we'll write down the values, the elements as is, 0, 1, 0, and then -1, 0, 1, and in the first row we have 1, 0, 0, and then -1, 1, 0. And if we were to draw a line along the major diagonal, we have 1s along the major diagonal, we have 0s along below the major diagonal, we have 0s above the major diagonal. Therefore, we have achieved the inverse matrix. This matrix is the identity matrix, and this on the right hand side is the inverse matrix. This is the inverse matrix, and therefore, once we have this inverse matrix, we should be able to find the value of this X matrix. The equation which we started off is this, isn't it? Matrix X. We can achieve that by taking the inverse matrix and then multiplying that by the constant matrix B. So therefore, the X matrix, we can achieve that, or we can achieve the values of X by taking the inverse matrix, which is -1, 1, 0, -1, 0, 1, then 6, -2, -3, and then multiplying that by the constant matrix, which is -1, 1, -2. -1, 1, -2. When we expand this one out, it is just a simple multiplication now. The inverse matrix is a 3 by 3 matrix. The constant matrix is a 3 rows and 1 column matrix. As long as the columns in the first matrix is equal to the rows in the second matrix, we can determine the size of this matrix, and the size of the matrix is going to be 3 by 1, 3 rows and 1 column. So we perform the multiplication here. When we perform the multiplication, 1 times -1 times -1 plus 1 times 1 plus 0 times -2. That is the first row, first column. Then we have -1 times -1 plus 0 times 1 plus 1 times -2. That is the second row, first column. And then we have 6 times -1 plus -2 times 1 plus -3 times -2. Okay, we can simplify this. When we simplify this, this is going to come out as follows. This simplifies to -1 times -1 will be +1. 1 plus 1 times 1 is 1, and then 0 times -2 is 0. In the second row, we have -1 times -1 is 1, 1 times 0 is 0, and then 1 times -2 is -2. And in the third row, we have 6 times -1 is -6, -2 times 1 is -2, -3 times -2 is +6. So we can simplify this some more. When we do that, 1 plus 1 is 2, 1 minus 2 is -1, and then -6 plus 6 cancels out, we are left with -2. So therefore, this is our answer. Therefore, we can come back here and then say, if x, the solution matrix is x is 2, negative 1, and negative 2. And what this means is that the value of x is equal to 2, the value of y is equal to negative 1, the value of z is equal to negative 2. So we've been able to successfully solve a system of linear equations using inverse of a matrix, So these are interesting problems, and inverse of a matrix is a powerful way of solving system of linear equations. We will look at some more examples in my next presentation.